Hi guys, so here we'll be learning about the relative strengths of acid. Here we're talking about the organic acids. That means all of them must have this functional group COOH. Let's put the R here. Now, what does it mean by acid? In this case, we are referring to the definition Bronsted Lowry acid. It means that, oh, by the way, this is not a cross. It's supposed to be an O with a stroke here. Bronsted Lowry acid means the substance could dissociate and give off H plus ions, which is acidic, and the other fragment. Now, this H plus must come from this single bonded oxygen of this COOH group. So what's left if I chop off this part would be R, C, O, O with a negative charge. Right. Now the thing is, what is varied is the nature of this R group here, the R group. Since we know that the O minus and H plus can be attracted to each other, then we can assume that this can go back to the original form, isn't it? Because there's charge attraction, there's also bond formation. So what makes it stay at this position will be how stable this fragment is on its own. And we call this the conjugate base. So it's very important to understand the idea of acid and the conjugate base theory. Now, how could we stabilize this conjugate base? Let's say our group is electron withdrawing. Okay, so let me just put here as electron withdrawing group connected to COO minus. Now we know that this negative charge is here and it could be delocalized onto the other oxygen this way. The thing is, when you are able to disperse this negative charge, it's more spread out. That means this oxygen is less likely to pick up this proton and go back. Because it's all spread out, it's not so concentrated. With the help of EWG, electron withdrawing group, which pulls electrons away, this is helping even further. Because this group here will pull electron density away from this region here and spread it even more. So that now this negative charge is very thin. So thin that it would not want to get back this H plus and go back. That means you stay here. And if you stay here, that means we can isolate H plus, which makes it a stronger acid. Now suppose we have R prime is an electron donating group. Electron donating group will push electron density towards this direction. So EDG push it to the carbon with CO minus. So this will intensify the negative charge onto this region, which makes it more negative and hence it's more likely to grab the H plus and go back and stay here as a molecule, which means that this equilibrium will not like to lie on this side to isolate the H plus. So in conclusion, we know that electron donating groups will decrease the acidity of a carboxylic acid, whereas electron withdrawing group will increase the acidity of carboxylic acid.